I'd like to welcome everybody to our August meeting of New Mexicans for Science and Reason. Little weird lighting today. Oh, here we go. Got my little setup here. Okay. Good to see everybody. So before we launch into tonight's speaker, I had a couple demos. We used to always, back when John Gohegan was running meetings, start them with a fun little science demo. So I hope these work. So I have the falling chain, and you do have to get it loose. It has to, if it's tied up, it doesn't work. Oh, and that thing has got a pretty good knot there. All righty. I guess the latest theory is that it's the chain that's pushing against the glass to make it go up. Okay, we got Randy. All right, almost got this thing untied. Okay. Whoa. Okay. Oh, alrighty. I'm gonna turn off the virtual background because that really affects anything that's not a human face. Even pens, you can do magic tricks by making coffee cups and pens disappear. Just low quality. Okay. Oh, so I'm loading the chain into the glass. Oh. Okay. Hey, just going to get this right up by the camera here and get enough to start falling off. Ooh. Well, you really have to slow those down. But we've got the Zoom, we've got the video, so you can watch it at home. The second was one of John's favorites, the Cartesian diver. I have a little submarine here, and we apply pressure. Here's Covan, excellent. So I'm going to apply pressure, and there it goes.
Correct me if I'm wrong, Dave, but I think the Cartesian diver is the same as Newton's thermometer.
Ooh. Well, I've always heard it called the Cartesian diver, but
yeah, but I mean the mechanism, the physics of it.
Oh yeah. So what's it called? Whose thermometer?
Oh, Newton's thermometer. So it's a series of glass spheres floating in water, and as the temperature changes, the density of the water changes, and one sphere will float up after another, and which spheres make it to the top reads out the temperature.
Tells you the temp. How cool. Well, there you have it. We're all a little bit smarter now.
But the first one, I'm sorry to say, I didn't quite get what
the chain. It's the so as the chain falls, I've got a picture of it in the latest newsletter. Okay. Need to
the trick is that we're surprised because so much of the chain will pour out when only a small bit was started. Is that it?
The trick is that you see quite a bit. I'm going to call up the
because I'm thinking what happens is we're weighing the little tag of chain that you dropped against the whole chain in the cup, but it's actually only being weighed against the little length.
There's a great series of videos on it by Steve Mould on YouTube, and it's a controversy that's been years running, and lots of pretty serious scientists have. Okay, I'm going to get over to Zoom and screen share. desktop. Okay. So here you're looking at the latest issue of NMSR reports, which is online, and it's got a new puzzle, got a cool triangle puzzle. Yes, here it is. So in this thing, you really have to have a decent room for the chain to fall unimpeded to get up to speed. I don't think I had that here with my laptop being in the way. But here you see this same gadget that I was just showing you right there in mode where the chain is falling and it just develops this gap between the chain and the glass. It's quite impressive.
I believe I can explain it, actually.
Oh, okay. Well, you got 30 seconds to explain it.
Okay. We think the little bit of chain that you dropped in the beginning isn't heavy enough to lift all that remaining chain out of the cup, and it's not. But it's only lifting the inch between the lip of the cup and where it's piled up on the bottom. That's all it has to lift. And as the part that falls faster and there's more chain outside the cup, it accelerates. As the speed builds up, that's enough to lift it above the lip of the cup and make it look suspended.
Well, that's interesting. I really encourage you to watch Steve Moltz, because it really, I think, might be a tad more complicated than that. But it's a fascinating series, and John liked it, and so we did it. There we go. We've got people in the waiting room. So all I have to do is figure out where they are. And here we go. Oh, John Durr is here. Okay. Austin Meady, welcome aboard. Okay. So any other comments before we get on with the main event? And okay. So Coffee has put a YouTube video. What's that one about, Coffee? In the chat, the YouTube video?
It's the one you were referencing. It says Steve Mold's video on this.
Yeah. Well, he's got several, but yeah, it's a fascinating subject. Okay. So our tonight we're sort of sharing speaking, but our esteemed member, Joe Archbold, is going to talk about his argument that there's a little more to look under the hood of wave particle duality. So, and then I've got a little presentation queued up, just a few slides, some from my class where I talk about quantum mechanics in my lecture on weird science. It's one of the last lectures of science and pseudoscience. And basically the quantum world is just so weird. I think it's interesting to bring up in the pseudoscience class, because the real strange things of science, like quarks and spooky action at a distance, they're a lot stranger than your typical pseudoscience claim of Bigfoot or vaccines causing autism or the Loch Ness Monster or what have you. So Joe, can you introduce yourself? And then and I've given you co-host power, so you got some slides to share. But tell us a bit about your background and all that.
Well, my name is Joe Archbold, and great to see you all. And I am not a brilliant scientist, but I do like to solve puzzles. And a puzzle that was bothering me for years was the weirdness of quantum mechanics. And I had a discussion with some of my friends. We used to meet for lunch once a month, and they were interested in astronomy and science. And we got talking about it one day, and I suddenly had an idea, and that was it. And I'd like to present a piece of that idea to you this evening, okay? And I'll be glad to try and answer any questions. I don't consider myself brilliant or in any way a real knowledgeable individual on science, but I've read a lot of books on it, and that's my introduction. So I have to go ahead. I have never done this before. I used to present for IBM when I worked for them for 30 years, but we always, in the old days, we always used overhead foils. We didn't have PowerPoint in those days, and we kind of stuck on it with it until I retired back in 1995. I guess I go to share screen right now. Is that correct,
Yes.
Dave?
Yes. While you're doing that, I'd like to point out that they have pictures of overhead projectors on Facebook now as contests for who remembers what this ancient thing was.
That's me. Share screen. Host disabled participant screen sharing.
What? Okay, let me try making you screen share again. Make a co-host. Try it now.
I'll try it again. I'll go okay, and I'll go more.
Here,
And
are
I'll
you clicking
go.
that little green share screen button on the bottom?
Okay,
of the
I've got it
Zoom?
on a. It's reduced, so I've got it on a little table. There it is, and now I'm going to share that waves and go over to share. Where? Hold on. There.
Oh, we see something. Okay.
Very good. Now what I would like to do is go to my presenter slide. Okay. And
whatever you did when we practiced this earlier,
yeah.
because that worked.
And I'll go to here and show presenter view. Okay, I see what I want to see, except I'm going to reduce you guys over here. Or let me see if I can reduce myself. Your pictures are all in the way of my verbiage.
Zoom does that. It really sort of inserts itself right where you need to click to do things.
Okay, well, okay, I'm going to get rid of that speech underneath.
There we go. That looks good.
And then I'm going to go down here. Oh, I know what I'm going to do.
I think if you can see your notes, we're all set. Just start.
No, I can't see my notes yet.
Uh-oh. Okay, we're not there.
But can you still hear me?
Oh yeah, you're coming through fine.
All right, we're just about there. Show grid video. Okay. Show small active speaker video. Hide thumbnail video. I don't want to do that. Oh, well, that made it worse.
Well, somehow you had it.
Oh, there.
Somewhere.
Now I got it. I just got
Excellent.
you on the screen. Thank you. Can everybody see?
We can see and hear. Sounds good.
Good. This evening, I want to take you back to a pleasant time at the beach, or maybe to your favorite pond or river. I always found it fascinating to watch waves breaking on the beach, or when I threw a pebble into the still waters of a pond. As the created waves spread out, I observed their inevitable journey to the bank. It provided a great sense of serenity and security that every pebble produced similar hypnotic results. The question is, are there any other waves that follow this pattern? And I would assume that we know there's sound waves and magnetic waves and tsunami. Of course, that's water again. And of course, earthquakes. And I'd like to ask you a question. How do those waves collapse when they encounter a barrier? Well, as I see it, they seem to collapse along their entire front or around the area of a protruding obstacle. Now, are there any other type of waves? Well, I think we all know there's a thing called a quantum wave. And the question is, how does it collapse? And I am told that it really collapses to a point. Now, I might ask the question, why is this the only wave that nature chooses to collapse to a point and not along its entire length or just at the location of a barrier? It is interesting, we only began to realize about this wave in the early 20th century when it discovered it does not conform to historic patterns. Well, the real answer is I've been hunting for it. Nobody seems to know. There have been some theories about many worlds and all of that, but I think most serious people tend to reject some of these ideas have come up. Yes, we don't know. We only see that nature does it that way. We see it with our own eyes. When we send a particle through slits, it immediately appears on our screen. Or does it? Einstein had a problem, of course, with this idea. If allowed, this expansion of a quantum wave would eventually reach a dimension where to collapse instantaneously, it would have to travel one end to the middle faster than the speed of light. However, since the experimental distances were relatively small and the speed of light so fast, this objection was generally ignored, and Einstein and Schrodinger seem to have lost that particular argument. Fine, no problem, let's press on. So this particle lands at some apparent random spot on our screen. However, when we send thousands of those particles through our double slit, one at a time, they are not random. They form an interference pattern. I got a little diagram here of the interference pattern. Most of the particle diagrams are slightly different. They're more compact with the towers closer together, and they tend to taper out as they reach the edges. But that's the whole general idea of an interference pattern. Now the question is, how does each particle know it should land in one of the cluster areas of particles and not between clusters of our interference pattern? Well, to do so would require each particle to have more computing intelligence than we possess. Yes, very sharp cookies, these particles. So is there a way to rationally understand what's happening or only appears to be happening? Can there be a way nature does not have to change its whole modus operandum for a quantum wave to exist? And the answer is a resounding, in my book at least, yes. Nature does not have to change. Therefore, let us treat QM waves just like all other waves, and let's see what happens. The apparent weirdness of QM comes from an atom's ability to have its electrons store varying amounts of energy. Each orbital of an electron can contain up to a quanta amount of energy or less. When that quanta is reached, the electron will jump to the next orbital, or if depleted, the electron will drop to a lower level. It will stay in that orbital until it can gather in one infusion or many the quanta required to jump to the next level or completely out of the atom. To quote Einstein in his 1905 paper on a heuristic point of view concerning the production and transformation of light, Annalen Physics 1905, there's the pages at the bottom there. He said the simplest possibility is that a light quantum transfers its entire energy to a single electron. We will assume that this can occur. However, we will not exclude the possibility that the electrons absorb only a part of the energy of the light quanta. So he is saying an electron can absorb little pieces of a particle. Yes, Einstein was aware that electrons could store varying amounts of energy. When an electron receives or loses a quanta of energy or matter for its current orbital, it jumps to a higher or drops to a lower orbital. But when it receives less than a quanta, nothing happens that we can detect till enough small bits are added to the electron to total a quanta of matter or energy and manifest itself as a quantum jump. I actually am surprised. I don't understand why Einstein did not use this more complex argument with Bohr at Solvay. That particles did not necessarily transfer all their energy to a single electron or atom, but might only surrender tiny portions of each electron or photon. Therefore, pressing on, if in the path of the interfered wave that exited our two slits, there was just one atom on our screen with an electron on the brink of jumping to a higher orbital, it would, when it received a small amount of energy or matter from this extended wave, jump to the next orbital. It would emit a photon indicating to us that a particle had arrived. This is not the particle we sent through the double slit. It is a completely new particle with just a smidgen of the original particle in its makeup. Electrons within an atom are being channeled or controlled are very compact waves and appear to be bullet-like particles. When free, their wave nature presents itself more fully and they behave like all other waves. By the way, there's an offside. At this point, it's easy to see why the English scientists in the early 1920s concluded particles were bullet-like, and the German scientists believed them to be waves, considering the type of experiments they conducted. Bohr's Copenhagen interpretation was, of course, particles were both. They had a dual nature of being particles and waves. Of course, my conclusions here are that they're definitely more on the side of waves than of particles, but they are electrons and fermions are pretty solid. Back to the screen here, the second paragraph. As waves, electrons can be split. Atoms and large molecules like Buckminster fullerenes or carbon-60 can also be split. This is not the same type of split as splitting the atom, where the forces within the atom are torn apart. The forces here are evenly split among the constituent parts, allowing stability. Those constituent parts we cannot observe, but are known as virtual particles as they pop in and out of existence with the addition or subtraction of matter or energy. And interesting note on the side here, may I add, it was not till 1947 that Richard Feynman first used the idea of vertical particles as squiggly lines in his diagrams. Fermion particles, having decayed from their normal detectable state, become virtual fermion particles. Though invisible and more numerous than solid matter particles, they continue to have mass. Though reduced, this mass still reacts to gravity and is an excellent candidate for dark matter. Instead of hunting for WIMPs, weakly interacting massive particles, they should be accepting VIPS, voluminous interacting virtual particles, as their suspects. In conclusion, quantum behave like all other waves. They can be added to and subtracted from other waves. They can be split longitudinally as they encounter atoms or molecules. And as demonstrated in chapter 2 of my paper, A Dublin Interpretation of Quantum Mechanics, quantum waves can also be split laterally, providing a logical explanation for many weird spin experiments. And you know about these different boxes that are Stern garlic type boxes that you use for electrons, and filters you use for photons. Splits of bosons, fermions, and molecules naturally are not the same as the splitting of the atom we are accustomed to in nuclear reactors and bombs. This new split divides the forces evenly and maintains a balance of force within each split, as opposed to shredding or ripping apart an atom. We cannot detect quantum waves other than to convert portions of matter to matter with matter or energy. Therefore, this hidden matter in waveform and as virtual particles is an excellent candidate for dark matter. Don't forget 6 VPs, or really VI VPs. This on the last page is a link to my paper. It's called Quantum Mechanics, a Dublin Interpretation with a Solution to the Measurement Problem. And underneath it is the link right to my paper in the Science Journal. I hope this presentation give you a heads up on the contents of the first chapter of my paper. The second chapter also considers wave splitting, only this time laterally between the transition points, i.e. the peaks, valleys, the positive to negative and the negative to positive points of a sine wave of a particle's rotation. Thank you for listening. And if you have any questions, I'll be happy to try and answer them. Thank you.
Okay. Well, thanks, Joe.
You're welcome.
I'm going to take your link there. I have a copy of the paper. Can you stop sharing for a sec?
Sure. How do I do that? Let me see.
There
I see it. Hold
red.
on. Hold on.
Yeah.
I'll get it there. How about that?
Okay. And let me fire up a Okay. Zoom does make it hard to see. Okay, I'm gonna minimize everybody for a second. Here is your paper. Yeah.
But by the way, if anybody wants a link, I can just send me an email and I'll send you the link back.
Yeah. I can put your email in there too.
The email is at the bottom of the screen too.
Oh, okay. There we go. And that was just about the last slide there. Okay. Uh-oh. Oh, here we go. Copy link. Okay. And let me get back to Zoom and full screen it. Chat. Okay.
By the way, Dave, can I copy this presentation?
Yeah, we're going to put it
computer?
on the yeah, we'll get a
but after the meeting,
copy.
you can tell me how.
We're going to have it on YouTube like we do all our presentations.
Oh, okay. That's good.
And then you'll have a link to it. And then, you know, if you need your own copy, we could figure out a way to.
No, that'll do.
They're kind of big to email. They're usually about 100 megabytes or so.
Yeah.
Okay. Okay, I've put the link to your paper in the chat. And while we're at it, let's just I'm gonna grab your email. Not letting, I'm just gonna type it. Archbold.
Right.
At flash.net. Yeah, okay. So I had a few comments. I got a neat picture of that double slit experiment. So can we just take a look at those and then we'll have a good old discussion? Does that sound all right to everybody? Okay. So what I need to do is open yeah. And well, I'm having trouble finding it. Let's see. Open. Okay. Movies. Here we go. NMSR. There we go. Okay. And there we go. Yeah, I've got a few movies too. So not now. I just wanted to run the slideshow. Okay. Can everybody see that?
Mm-hmm.
Okay. So oh yeah, before we get going on the quantum, this is one of the slides I show for weird science, showing basically in the heart of an atom, a proton and neutron essentially exchange quarks. You could consider that the neutron sends a down quark to the proton sends an up quark to the neutron, transforming the proton into a neutron and the neutron into a proton. And that's what we call the strong interaction. The only problem with this is we've got the up and down quarks crossing like ships in the night, and you can't have isolated quarks. So the conventional explanation is no, it's not this with up and down quarks going in opposite directions. It's this. You could consider the down quark going backwards in time, except it's an anti-down quark, and that combination of the up quark and the anti-down moving together, we call that a pi meson or a pion. And this one happens to be a positive. You could just as validly consider that the up quark is going backwards in time and it's an anti-up, and the anti-up and the down quark together form a negative pion. And to me, this is the just about one of the weirdest things of modern science. That at the heart of matter, we've got these little particles we can't ever isolate going backwards in time. And that's why we can have gold and oxygen and nitrogen and planets and humans and giraffes. Don't forget giraffes. Oh, and here's the delta, a particle that actually has a charge of 2. And when it decays into a proton and a pion. And just look at which way those anti-downs are going. They're going backwards in time. So Max Planck, of course, kicked off the quantum, and for him, it was more like a mathematical way of combining these black body curves, the high frequency and the low frequency black body curves, to a single equation that it worked on all frequencies. And so he came up with these little quantized bits of energy. But it turns out that energy and light are quantized photons. Light is quantized, and that means light is itself both a wave and a particle. We call those particles photons, but it's not just electrons that are capable of being wave and matter. And in fact, a bullet, it has a wavelength. It's just incredibly small. But these, you can see quantum transitions. Here's how to make a diffraction grating from your DVD disc, and that's looking at mercury vapor right there. So let's get into wave particle duality, and here's that famous electron gun experiment. On top, light waves on the bottom, and the light waves do form an interference pattern, as would water waves or sound waves. But curiously, the electrons do form a interference pattern. And so I've got my first little film, the controlled double slit electron diffraction. This is one great little movie. Controlled, here we go. And play and begin. So what we're seeing here is individual electrons in real time, and they're going through what we think are both slits, but they land on this screen and make a little spot of light when the screen detects them. So they are not measuring which slit the electrons are going through. Now it's speeded up, so it's sort of like a time lapse thing, and we can sit back and watch. This experiment ran actually for hours and hours, I think 5 hours. So yeah. So now we can see the interference pattern forming. So basically, and Feynman has a pretty good explanation of this, but it is mind-boggling, or mind-gobbling, as I sometimes say, to think of how could something be two such different things, one that spreads out and another that hits you like a bullet. How does that happen? So there we go. There's our film. Okay. And
In this presentation, Dave, do you have a citation of the paper?
of this controlled double slit electron?
Yeah.
No, I need to find that. But yeah, I saved the video. Wow. So basically, when we look at this through what we've come to know as quantum mechanics, when we say which slit is used, both of them, if we try to detect which slit an electron is passing through, we'll always find whole electrons or no electrons at all. But then that destroys the interference pattern also. But I love this little road sign for this quantum junction, get in both lanes. And that shows how just bizarre and non-intuitive this whole concept is to our macro sensitivity. I certainly wouldn't want to see a sign like that on I-25. So Isaac Asimov had this analogy where he pointed out, hey, you've got a 3D cone. If you look at it from the top, it looks like a circle, but from the side, it looks like a triangle. So is it a triangle or is it a circle? And the answer is yes, it's both, depending on how you look at it, how you measure it. And waves and particles are like that. Some experiments tend to bring out the particle nature of these quantum objects. Other experiments are better illustrated to show the wave nature, but photons and electrons are quantum objects, and they are both waves and particles. So
Hi,
here's
Dave, if I
Yes.
may refer
Yes.
you back to the previous, well, the third one back from here, where you had the road splitting in two and the particle. If it was a wave rolling down the street, okay, and the street was in a valley, and it came to two junctions like that, the wave would have no problem going down both paths.
Okay.
Yeah, so I just thought I'd mention that.
Yeah.
You're talking about a classical wave. We're talking about quantum waves, not the same
Yeah.
thing.
And electrons, which I don't think you can have half an electron. You've
Right.
got a whole electron or nothing.
Well, what Joe was quoting at the very early part for Einstein in a 1905 paper sounded like you could have fractional electrons. And I have a follow-up question to that. Did he repeat that same sort of argument later, say after 1925?
No, he didn't, and that always surprised me.
Well,
Okay.
in 1905, he also published a paper which explained the results from, Leonard, German physicist, had been doing photoelectric measurements, and he found that you didn't get any photocurrent out until the energy of the electrons being emitted to the surface were above a certain level. And that contradicts, if you match up the energy flux, that contradicts that quote, or what Einstein was saying in that earlier paper, both of those 1905 papers.
They were amazing, seminal papers, but yeah, he
I don't
he
recall
went on
that.
and kept learning new stuff. Yeah.
Yeah, I don't recall that quote that Joe gave might be that same paper, but I don't think they were looking at the quantitative aspects of energy transfer at that time.
Yeah.
And that might have been a first attempt to explain the essentially the work function of conducting surfaces, and that. But then the sub work function electrons would not accumulate energy and finally squirt out. These were photons anyway. They were incoming, and then electrons were coming out. And that paper was commonly accepted as being a demonstration of the opposite part of photons. That is, they're quantized by Mach's arguments, but the coupling to electrons is also quantized. You have to have enough energy in the incoming electron to bump a photon, a photo electron out in the incoming light. I'm sorry, I messed that up. But anyway.
And switched.
Yeah.
Well,
anyway, I'm not familiar off the top of my head right now. My memory is not what it used to be. And but that argument about fractional storage of energy, and then it suddenly pops out a photon, doesn't strike me as being right. And I just wondered whether Einstein had repeated that kind of argument, because he continued to talk about some aspects of the quantum mechanics of particles later in life. And,
right. He never did figure it out, though.
Yeah.
There was some parts of quantum he never accepted.
Yeah.
What's that?
And he never accepted it either.
Well, yeah, no, but
yeah,
he had some counter examples that do cause people to scratch their heads. Entanglement, is a head scratcher.
Yeah.
Well, if you read my paper, I may be able to explain that as well, at least my idea of what entanglement is. Okay.
I could.
This wave presentation was just a little small presentation to give you a feel for what was kind of the main topics of my first chapter. The second chapter, of course, dealt with all the weird spin experiments and how they come out, and they're totally opposed to your intuition. And that can be very nicely explained by the splitting of particles. Okay. So I talk about that in the second chapter.
Okay. So I could make a copy of this presentation, save it as a PDF and put that on our website also. Would that be okay, Joe?
Oh yeah, you're
that
welcome.
way people could look up that quote from Einstein and
yeah, if you want to, or if you want to call me or ask me any questions, I may not be able to answer. There's a whole bunch of stuff I don't have the foggiest notion of. Okay, but the stuff I've written about, I've kind of researched it to the best of my ability over the last 15 years. And well, not 15, it's about 10 years since I started talking with my friends up in Michigan at our lunches up there.
Okay, well, I'm going to press on because I think I've got some slides that are pretty relevant to a couple of the things you said.
Yeah.
But on the way there, we've got basically this roulette wheel concept of superposition of states, and rather than saying that the ball is racing around the track, which might be a classical physics approach in quantum mechanics, we just consider this system as a superposition of all possible states. So it's analogous to the ball racing around the track, and when the ball lands, that's like collapsing the wave function, making a measurement. So Heisenberg's uncertainty principle does play into the double slit experiment. So if we're going to look at an electron, the photons that we look at that electron with are going to make it ricochet. They are going to impart momentum. And so it turns out the better you know a particle's position, the worse you know its momentum, and vice versa. And there's the famous uncertainty principle equation. Basically, uncertainty in position times the uncertainty in momentum, or speed, if you were, is bounded by Planck's constant, h. So that's a very small number. I think I went a little too fast there. Okay. So I got out my trusty Feynman lectures on physics, volume 3, quantum. And in his introductory chapter, he said, hey, here, this is quantum mechanics. The probability of an event in an ideal experiment is given by the square of the absolute value of a complex number phi called the probability amplitude. And so P is the probability, phi is the probability amplitude, and probability is the square of the absolute value of phi. And it's a complex number. When an event can occur in several alternative ways, the probability amplitude for the event is the sum of the probability amplitudes for each way considered separately. And there is interference. So here, the probability amplitude is the sum of two maybe interfering probability amplitudes, and the probability of the event is the probability of that sum, absolute value squared. So if, and this is number 3, an experiment is performed which is capable of determining whether one or another alternative is actually taken, then the probability of the event is the sum of the probabilities for each alternatives, and the interference is lost. So in the double slit experiment, this is where the electron, we don't know which slit it goes through. It seems like it's going through both of them, but it interferes with itself even. And there you have this, and we get our sort of classic interference pattern of the electrons. If we pay attention to which slit those electrons go through, then we lose the interference pattern. And the way to think of that with Heisenberg's uncertainty principle is, if you don't care about which slit the electrons go through, we're not measuring, then you have this situation, number 2, the probability is the sum of the interfering amplitudes, absolute value squared. But if you look at one of the electrons as it's going through the slit to see which slit it's going through, that is going to cause that electron to ricochet, and it's not going to go where it needs to be to create that interference pattern, and the interference pattern basically is lost because of Heisenberg's uncertainty principle. So I hope that's making sense.
Yeah. By the way, Dave, if I may,
yeah.
at this point, I do not, and I mentioned this in my paper very emphatically, the mathematics of quantum mechanics, I think, are absolutely fantastic. And I have no argument at all with any of the mathematics that's being done, or how Schrodinger's equation works, or whatever. I just want to let everybody know that. My question is just the interpretation of what's happening with what we see, not what is sometimes really happening. Okay.
Yeah, it's a great question. So this next figure shows the methane, or no, it's a NH3 molecule. Yeah. And the ammonia molecule. It's rather stinky, but it can have a dipole moment on the left with the nitrogen sort of above the 3 hydrogens. The dipole moment is down. On the right with the nitrogen on the bottom, the dipole moment is up. And so that's 2 states. And there's, 2 ways to get from A to B. We could take the whole atom and turn it over. But there is an extra way, a quantum mechanical way. Basically, you could think of this nitrogen tunneling right through this barrier of the 3 hydrogen protons and ending up on the other side. And it actually happens. There is a small probability of that happening. So Feynman adopts this as a great example of a quantum mechanical system with two very simple states: spin up or dipole down. So and here in this equation, he talks about shining a light on such a system, and here's this rather intense integral, and we can see in here that the frequency of the photons, we're looking at a spectrum of these spread out wave photons. Back in our physics days of studying electromagnetic pulse, we described the broad spectrum as DC to daylight, almost 0 frequency to maybe as fast as light waves or even higher frequencies. So so here in this basically equation for what's the probability of that methane molecule flipping quantum mechanically by the nitrogen tunneling through the atom, there it is. But generally they do an approximation, which is replacing the actual function by its value at the center of this very sharp resonance curve, and then you get this simpler equation, which basically would tell you when you shine some light on this methane molecule, it could flip. Or the ammonia molecule, sorry. So here is the transition probability for the ammonia molecule as a function of frequency. And basically on the right, it shows that this spectral intensity can be approximated by the value at the center frequency. But what's important about this to me is this says, well, because I was thinking, it's important to note, oh man, yeah, so right here, this is the general theory of the absorption of light by any molecular or atomic system, such as light hitting a hydrogen atom and making the electrons jump different orbitals. In the slit experiment, really there are no orbitals. Those electrons are just shooting through space, going through slits. But here we can see that basically here's the probability for this flip happening, and if the frequency of the light is omega naught, yeah, it's probably going to happen. But does the light have to be exactly that frequency? No. We can have we can see there's a distribution, and there's a small probability that you could have this frequency omega plus quite a bit, and you could have that higher frequency light or this lower frequency light cause the transition. The probability of that is much smaller, but it is non-zero. Now you get to here, these intermediate frequencies, the probabilities are very low that you'll flip those nitrogen or the ammonia atoms. So basically, this to me shows that you don't have to have exactly the same energy as is required to make the electron jump, but it better be pretty darn close, or there is going to be no transition. And so I got some videos, and I think the most important one, I don't know if we're going to go through all of these, but this one, Bohr's model explained in 1 minute, has a very important little, I thought, point to make. Open file. 1 minute. All righty, and here we go.
Today we're going to talk about the concept of Bohr's model. Bohr's model deals with hydrogen atoms or hydrogen-like atoms, basically scenarios where we only have one single electron. Now what Bohr's model states is that we can take a light and shine it onto this electron. If this light has a sufficient amount of energy, this electron will actually absorb this photon of light and will cause the electron to jump up to a higher energy level. So in this example, the light was sufficient enough to cause the electron to do a quantum jump from energy level 1 to energy level 2. Now if you just leave this electron in an excited state without adding any more energy to the electron, eventually the electron will jump back down to the first energy level and emit a photon of light. Now, what do you think would happen if we shined a light onto this electron and the photon had enough energy to get the electron past the second energy level, but not enough energy to get it to the third energy level? Well, you might be surprised to hear that absolutely nothing would happen, because light and the Bohr's energy levels are both quantized. If the photon's energy is not precise, then the electron is not going to jump.
There you have it. So that sort of argues against the idea of just accumulating enough energy till you finally get that jump. No, you've got to have a photon of pretty close. I mean, not exactly, perhaps, as that chart I just showed. I did want to show.
Steve, because I wanted to ask that same question of Joe. You
Yeah.
had mentioned that the electron could absorb lesser amounts of energy and gradually accumulate enough to jump. But I had thought the entire point of quanta was that it could not do that.
The thing about quanta is it's like a dollar. Dollars bills.
More like
coming-
a silver dollar, though, right? You can't
No,
break it.
it doesn't matter. Paper, silver if you want. Yeah. But it comes in a quanta. Okay. However, it's not the only money. Okay. I can have $1, but I can have 100 cents. Okay. So what I'm saying is the electron needs $1 in there. Okay. To be able to jump to the next orbital. Now it can get that by giving it $1, or you can get it to jump by giving it over time 100 cents.
I'm following that part, Joe, but here's the part I'm not following. I thought the jump from one electron orbital to another was a single quanta, a penny, not $1. That is the smallest unit that cannot be made into change.
It's always a electron when it's in an orbital. When it gets a quanta, it's going to jump. And always when it jumps from that orbital, you'll only get that quanta. That's what quanta is. And if it somehow or other receives that amount, if it already has 50% of that amount and it gets another 50%, it will jump. Okay.
I think we're talking past each other, but I think Dave understood the question I'm asking.
Yeah, sorry. Dave, did you understand? I'm sorry.
I think I agree with Coffee that in the energy levels, a penny is the better analogy for making an electron jump from one level to the closest nearby level. You can't break it down any smaller. There's no fractional pennies that are ever going to add up to make a penny.
No, but there are fractional dollars. And
Well,
the penny is the fractional.
But that's just a lot a lot of pennies. It's just more of you're maybe jumping 5 levels instead of just 1.
No, you just,
But it's still going to take a quantum amount. So I'm just
So your
disagreeing
theory,
with the
your
part
theory, Joe,
where
depends on there
the
being
electron
fractional energy levels.
can absorb energy over time and then suddenly release that energy when it gets enough. I think, you know, the way quantum mechanics works, you can expose that electron to all sorts of different frequencies, and if you get one close enough to the right frequency, pow, you're going to get a photon that is you're going to collapse that wave function and get that electron to make a quantum jump. But it's as that little movie showed, if you give it more than that energy, but not enough to get to the next level, it's going to be too far to make the first jump, not far enough to make the second jump. Nothing happens. You don't
that is
absorb energy
exactly
over
correct,
time.
Dave. Okay.
Okay.
And the electron has a certain frequency when it's in an orbit. You can only give it that frequency for it to be added to that electron. No other frequency will fit in there. So you have to have a specific frequency, and that frequency can come in bits or it can come in one chunk.
And I think I want to make another attempt
chunks
on that earlier Einstein paper on the photoelectric effect. You could shine photons of energy less than the work function of a given thing like sodium, and all day, all week, all year, and electrons do not come out.
Right.
You have to give the electron, the photons enough energy that it will come out in one whop, and it will come out with enough energy in the photon to make the difference between the work function and the energy of the incoming electron. I'm sorry, got it wrong again.
Yeah.
The photoelectron will come out with an energy that is equal to the energy of the photon that came in plus the work function, or minus the work function. That is, the work function is the work to get it out of the out of the metal, which the electron is kind of quantized in, but not like in atoms and molecules, because electrons in metal are kind of smeared out all over, and you don't know which electron is going to come out. But an electron will come out when you get the energy of the photons high enough, and nothing comes out if you send in a bunch of photons less than that energy.
Correct. I agree 100%.
A similar thing goes around the other way too.
Yeah.
All righty. We've got a couple more.
No argument there.
Okay.
Okay, I'm going to show, I think this is Richard Feynman on quantum mechanics.
Suppose that little things behaved very differently than anything that was big. Anything that you're familiar with. Because you see, as the animal evolves and so on, and his brain evolves, it gets used to handling, and the brain is designed for ordinary circumstances. But if the gut particles and the deep inner workings were by some other rules and some other character, they behaved differently, they were very different than anything on a large scale, then there would be some kind of difficulty in understanding and imagining reality. And that difficulty we are in. The behavior of things on a small scale is so fantastic. It's so wonderfully different, so marvelously different than anything that behaves on a large scale. You say electrons act like waves. No, they don't exactly. They act like particles. No, they don't exactly. They act like a kind of a fog around the nucleus. No, they don't exactly. And if you would like to get a clear, sharp picture of an atom, so that you can tell exactly how it's going to behave correctly, and have a good image, in other words, a really good image of reality, I don't know how to do it. because that image has to be mathematical. We have a mathematical expression, strange as mathematics, I don't understand how it is, but we can write mathematical expressions and calculate what the thing is going to do without actually being able to picture it. It would be something like a computer that you put certain numbers in and you have the formula for at what time the car will arrive at different destinations, and the thing does the arithmetic to figure out what time the car arrives at the different destinations, but cannot picture the car. It's just doing the arithmetic. So we know how to do the arithmetic, but we cannot picture the car. No, it's not 100% because for certain situations, a certain kind of approximate picture works. That is simply a fog around the nucleus that when you squeeze it, it repels you, is very good for understanding the stiffness of material. That it's a wave which does this and that is very good for some other phenomenon, all right? So when you're working with certain particular aspects of the behavior of atoms, for instance, when I was talking about temperature and so forth, that they're just little balls is good enough, and it gives a very nice picture of temperature. But if you ask more specific questions, and you get down to questions like, how is it that when you cool helium down, even to absolute zero, where there's not supposed to be any motion, it's a perfect fluid that hasn't any viscosity, has no resistance, flows perfectly, and isn't freezing? Well, if you want to get a picture of atoms that has all of that in it, I can't do it, you see. But I can explain why the helium behaves as it does by taking my equations and showing that consequences of them is that the helium will behave as it is observed to behave. So we know we have the theory right, but we haven't got the pictures that will go with the theory. And is that because we're limited and haven't caught on to the right pictures? Or is that because there aren't any right pictures for people who have to make pictures out of things that are familiar to them? There's still a school of thought that cannot believe that the atomic behavior is so different than large-scale behavior. I think that's a deep prejudice. It's a prejudice from being so used to large-scale behavior. And they're always seeking to waiting for the day that we discover that underneath the quantum mechanics, there's some mundane, ordinary balls hitting or particles moving and so on. I think they're going to be defeated. I think nature's imagination is so much greater than man's, she's never going to let us relax.
Wow. Okay. All righty. Oh, I did have one more pretty good video, and then I think I'll stop with that one. And that is Professor Dave, wave particle duality and the photoelectric effect. This guy has a YouTube channel where he discusses popular science, and he's also a flat earth debunker.
Hey, it's Professor Dave. I want to tell you about wave particle duality.
He knows a lot about the science stuff. Professor Dave explains.
So let's take a break from atoms and look at something else, light. For some time, we had known light to behave as an electromagnetic wave. For this reason, light is also called electromagnetic radiation. Light waves have both a wavelength, the distance from tip to tip, and a frequency, the number of waves that pass by a point per unit time. They are inversely proportional, since the shorter the wave, the more of them that can go by per second, resulting in a higher frequency. These variables are related by the following equation, in which c is the speed of light, about 300 million meters per second, the speed limit of the universe. The electromagnetic spectrum shows light of all the different wavelengths, from gamma rays to radio waves, including this tiny sliver in the middle, which is visible light, the light we can detect with our eyeballs. The wave theory of light was very useful for a time, but it could not explain the photoelectric effect. This was the observation that if a certain metal plate is irradiated with light, an electron is ejected, which can be detected when it interacts with a positively charged wire or plate sensor. The incongruity was that the ability of the light to eject an electron depends only on its frequency and not its intensity. So if the beam was below a certain frequency, even a very intense beam with a lot of light could not eject an electron, whereas above a certain frequency, the faintest beam possible could do it. This seemed strange, and a famous fellow named Albert Einstein solved the problem by extending a concept developed by Max Planck just 5 years prior. Planck proposed that energy is not continuous, but rather is quantized. That is, all energies are multiples of the smallest fundamental unit of energy, the Planck energy. In fact, quantum theory went on to show that everything is quantized, space and time too. So you can't infinitely subdivide them. You'll eventually get to a smallest thing that can't be divided further. But more on that in the physics course. Einstein extended what Planck said about energy and rationalized that light must also be made of quanta, which he called photons. These are particles of light. This explained the photoelectric effect because an electron is ejected when struck by a singular photon with sufficient energy. It only takes one photon, so even the faintest beam above a certain frequency will be able to do it. But if none of them are of that minimum energy, no matter how many photons strike the sample, an electron will not be ejected. It was found that the energy of a photon can be given by the following equation according to the frequency of the photon and Planck's constant. We now have to accept that light obeys wave-particle duality, meaning it is both a particle and a wave at the same time. Confused? You should be. This is the first discovery in a series that brought about the quantum revolution, completely changing the landscape of physics and how we view the universe. Newton's laws no longer reign supreme in the world of the very small, and the universe became much stranger almost overnight, thanks to Einstein and others that were inspired by him. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All righty. And let me.
Dave's Lou.
Oh, that's a different one. Okay. So I had a great little clip. I can't find it right now, but it was really old and hard to hear. But it was basically Feynman saying, at one time there were only, 12 people that understood relativity, but how many people understand quantum mechanics? And he said, nobody understands it. The math works, but nobody really can explain in picture form why. So let's see here. Slideshow. So here's a quote of Einstein's. I like to think that the moon is there even when I am not looking at it. And I see exactly where he's coming from. Little picture of the moon I took one nice sunny morning. So quantum mechanics has brought us all kinds of things, tunnel diodes, lasers, quantum cryptography. So yeah, let's have any more questions that we got. I'm gonna stop screen sharing. Okay. Got some new messages. Okay. So Gerry mentioned in the chat that the Weinberg paper that he talked about on the phone, we had a phone call earlier. What happens in a measurement, Stephen Weinberg. So that looks interesting, and that's in the chat. All righty.
I would just like to add something to my dollar and cents analogy. A electron in one orbital is like having a dollar and cents. Electron in the next orbital might be like having a pound and pennies. You need to have pennies to make up the pound in that second orbital. In the first orbital, you need to have pennies to make up the dollar in that first orbital, okay? You can have pennies come in 2 at a time, 4 at a time, or you can have 100 come in 1 at a time, and whoopee, that dollar goes shifted and magically it becomes a pound, okay? That's where my analogy stops, is the difference. But I'm just trying to tell you that the energy required in each orbital is different. So the frequency you need, I agree 100%. You have to have that frequency for that electron in order to give it the oomph it needs and allow it to escape. But my argument is just, you can have this come in. You don't have to have it come in all at once, but it's like Einstein says, you can have bits and pieces come in. And eventually, when you have enough of these bits and pieces that make up the quantity that that electron needs, it will get shifted out. Thank you.
So that makes a predictable, a testable prediction, which is that if you took, let us say, a wavelength that had 1/5 of the energy you need, when 5 photons have hit the electron will jump up. But that's exactly what we heard does not occur.
No, I'm not saying that. I'm saying if you have the frequency, the sense, okay, the frequency you need, you can have the frequency you need, but that frequency can be split. You need not get all the energy of that frequency. Okay.
I think, Joe, that I'm understanding you better than you're giving me credit for.
Well, okay.
And listen carefully to what I'm saying. You're
Yeah.
saying the frequency can be split. Let's say the frequency that you need is 10. You could give it 2 5s. And I realize I'm
No.
going the opposite direction. But that is what you seem to be saying.
No, I'm not. I'm
Well,
not saying
explain it
anything
with-
about the
With
frequency.
an analogy like that.
Let me put it this way. The frequency is this way. Okay.
Yeah, I know what a frequency is.
Now, the whole potential of energy is not just this way, it's also that way. And if you slice it and you just give it this little piece of frequency, the frequency is there, that goes into the electron, but it doesn't have enough overall power to get itself out. So these are the 100 cents that are chopped up that make your dollar. Once you get to the dollar area at the right frequency, you're out of there. I hope that helps you now, does it?
Joe?
I'd be the first to agree. I'm not physicist enough to arm wrestle you on it.
Yeah, I may be then, and so is Dave, and Coffee is too, really. The point of the photoelectric effect is it takes a photon with a minimum amount of energy coming in to eject an electron.
Yeah.
And anything less than that, you can take a half of a photon, which is, half the energy of the minimum photon, and you can shine all day long, all year long on that sample, and no electrons come out.
I'm sorry, I think you missed my point. And
But you're
I've
talking about
done my
orbitals.
best.
You're talking about orbitals, and in the case of metals, they are not in orbitals associated with a nucleus. They are, Feynman said it isn't this way, but it is kind of like this. They are spread out throughout. They are not bound to any particular nucleus. They form a sea of electrons. They are.
I agree, but still,
quantized
according to De Broglie, okay, each one has a complete in its makeup around has a complete unity of frequency as it goes around the atom. It doesn't end up missing at the end. It comes to a perfect join. Now that can expand and contract around the atom, but it is a definite state that each of those electrons are in.
I think you're being misled by the old quantum theory. That was supplanted with a lot of extra stuff when they went to quantum mechanics and the wave mechanics and the matrix mechanics, which are just two different ways of looking at the same thing.
Yeah.
And the point is, the interactions are quantized, and you can't take you can talk about a dollar and pennies and a pound and pence all day long, but there are no pences that are observable. There are no pennies that are observable in this analogy. They are quantized. There's only one kind of electron. Well, it's not quite right, but anyway, you can't divide an electron up easily. I'm not sure if you can't, but not easily, certainly.
Let me just leave
and the
you with
interactions
this.
are all quantized. They're
Yeah.
quantized electrons in and photons out. They're quantized photons in and electrons out. They're all quantized. There's no halfway in between or a hundredth of a way in between. They're all quantized.
I
Can-
agree.
That
The
gives you
electron
puzzling
stays in that
behavior.
orbit as long as it doesn't have enough energy to get out.
No,
And it needs a quantity of energy to head out. I agree
it needs
entirely.
a specific quantum of energy in one interaction. Not a little bit here and a little bit
Now,
there.
can you prove
If
can you prove that to me?
it's been proved
Because you
all-
can't, nobody has been ever able to see what's in an electron. And nobody's been ever able to tell.
they're quantized.
why-
You're right. Well, they
You know,
have some
So
properties, but
what I am doing is I am looking at the original idea
yes,
that we
but
put
first
in
of all,
we
you're
put an
looking at the
electron.
old Bohr theory, and that has been supplanted. It didn't work beyond hydrogen, and it didn't even work there without some extra whistles and bells that are not contained in it. The spin was not contained in it until you lever it in. And when you go to 2 electron atoms like helium, it was very hard. Go to 3 like lithium, boy, you got a problem.
Oh, I
The
agree.
old Bohr theory and orbitals of waves going around in an orbit, and they match up, and that gives you the quantum condition.
That reminds
went out
me of Newton. He could figure out the orbits of 2 planets, but when you put in a third, he said, "God, that makes your head hurt."
Yep.
And I know how it hurts
Yeah.
because I agree with you 100%.
Yeah.
So I've got
Arnold
a
Sommerfeld tried to solve these bigger problems, and he was not successful.
Yeah. May I
They
make-
all waited for the real quantum mechanics, Schrödinger and Heisenberg, to come on, and that solved the problems until you got to things like electrons, and Dirac had to, put his 2 cents in with. Anyway,
May I
you
just
haven't convinced me.
May I just, and that's fine, okay? May I just finish on one note? There is this idea that a particle goes through 2 slits somehow or other, okay? And interferes with itself on the other side and ends up on a screen. How do you explain where it ends up on that screen? It looks like random at first, but as you showed, Dave, they're mostly in columns. They're interference patterns. So
Exactly.
how did that particle know I should end up not in this bare area, but I should end up more often in this column area? Now, if you can explain that, then I say good luck. My paper
I can do
is
no
an
better than
attempt
Feynman.
to
The
explain it.
equations
Joe?
show that to you.
The uncertainty principle does explain that. When you just don't care which hole the electrons go through, that's when you get the interference pattern. When you start measuring which hole the electrons go through, you affect the electrons, and that destroys the interference pattern. It's the uncertainty principle.
That is not what I'm talking about, Dave. I'm talking about non-obstruction, a particle going through two
Well, I'm talking
slits.
about how the electron is supposed to know
And
where to go. It's just the interference pattern is destroyed when you use photons to try to look at those electrons.
well,
So
why
which
does
is
it
relevant?
end up in a cluster area instead of that?
Because that's the quantum distribution of individual measurements.
But
Each
point of-
electron making a spot on the screen
Well,
is an individual measurement. And you don't like the idea of the wave function collapsing, but that's what happens.
so I've got
It
one.
localizes at that point.
oh yeah, I believe it collapses, but I believe it collapses all along. But what I would ask you gentlemen to do is just read my paper, and you're certainly fine if you don't agree with me, okay? And I'll respect that, and I respect you all, and especially you, Gerry. You know a hell of a lot of stuff that I don't know, okay? And
So
I've
does
just
Dave.
concentrated on one little section. And I would just ask you to just think it over for a while and see what you think of it, okay? Especially after reading chapter 2.
Okay. So I'm showing a picture of the hydrogen atom, and what we've got is for this lowest level 1, 2, 3, 4, 5, and these are all ultraviolet. They're short frequency transitions, and then from the second level we got 4 the Bomber series. These are the visible hydrogen lines, and then for the third electron level and up, we've got these 3 Passion series, which are actually in the infrared. So, but basically, these are the pennies, I think. You could
No,
just
no.
each one of these wavelengths, which also has a frequency with it. Those are the pennies. So we got 1, 2, 3, 4, 5 plus 4 plus 3. That's 12 pennies. And I don't, if you could help me understand what you're saying, if you could show me in this diagram what are the fractions of pennies that would go into this anywhere.
You see the 122?
I do, yeah.
Okay. The 122 are pennies. Every penny is a 122, and every dollar is a 122. We're just putting in sometimes only part of a 122, but we're not changing the frequency. We're just changing the amount of frequency. As you know, waves spread out. The frequency is going this way, okay? But the wave continues to spread out. The frequency stays the same, but the amount of energy in any particular part of that wave is reduced as it spreads out. And what I'm saying is some electrons can get this little slice. They need this amount to jump.
Let
If
me
they
try
only
this,
get
Joe.
this amount, if they only get this amount, the electron can store it. And if they get another amount, they can store it. They can store it all the way up until they get the whole amount. When they get the quanta that's required to eject, the electron gets out of that orbit.
I think I understand what you're saying, Joe. Let me try this. I don't
Yeah.
think it's going to fly though, but I'm going to try it.
Yeah.
You're imagining the wavefront as a long wavefront, like a wave approaching the
Yeah,
beach.
like a normal
And the
wave on
electron
the beach.
is
Yeah.
like a pebble on that beach.
Yeah.
Each shadow, it casts a shadow because it absorbed part of that long wavefront. And the rest of the wavefront still hit the beach.
Yeah.
And
Right.
multiple wavefronts keep transferring energy to the pebble. But I do not think quantum scientists would agree that that model applies here.
That's what I'm arguing about, is what everybody believes.
So if you want
And
to
how
challenge
can
the existing
everybody
model,
believe
if you want to challenge the
something that's
existing model,
ridiculous?
can you make a novel, testable prediction that would demonstrate that we've had the wrong picture in our minds? Well, I shouldn't say we, because I'm not in the club, but real physicists.
Let me just say this way. If you look at the way I'm approaching it, it explains without any weirdness and the way all other waves behave, how quantum works. And if you look at my chapter 2, I say not only can waves be split along their whole length, okay, they can also be split where the wave function goes up and down. They can be split at their peaks. They can be split at their bases. They can be split at their transaction points in between, okay? And that explains why you have so many weird outcomes that are not explained in spin experiments. They say, well, that doesn't make sense. But if you look at it, that an actual, they have these boxes, for example, in a Stern-Garlick, a box can be considered for electrons, a Stern-Garlick experiment. You have electrons coming in one aperture, okay? And you have two other apertures. You have spin up electrons coming out the top, and you have spin down coming out the bottom, okay? Now, what I've done is I've colorized those, because if you turn the magnets 90 degrees, okay, then you get different spins, okay? But you only get two, you get spin up and spin down. But really what you're getting is two different spins. There are a total of 4 different spins in any Stern-Garlick experiment, one with the magnets horizontal, and or 2 with the magnets horizontal and 2 with the magnets vertical, okay? And those 2 boxes, Albert, what's his name? Albert was, Dr. Albert wrote a book, Quantum and, I can't remember quite the name of it right now, and experience, quantum mechanics and experience, okay? And he talked about these boxes, and he says it doesn't matter what type of particle you're talking about, okay? The inners of the boxes would be slightly different, but they do the same thing. If you put protons into one box, you'll get 50% of electrons coming out this way and 50% this way. If you put in all electrons of the same spin, then they'll either 100% come out here or 100% come out there, depending on what spin this one had going in, okay? What my take is, these boxes do not split or do not sort electrons. In other words, when one comes in, they send it this way, and another comes in, they send it this way. But I'm saying that each electron or photon that goes into these boxes gets split itself in half. And the reason I say that is because if you do this millions of times, okay, you will always get exactly 50% coming out the top and 50% coming out the bottom. Now, if you bring it down to lower number, okay, the hundreds and stuff like that, you should have a discrepancy between 50%. It should be maybe 50.00005 here and 49.00005 there, okay, for that one. But you don't. You always get 50% coming out the side and 50% coming out the bottom. If the electron is of the same color as the box, then you will always get 100% either coming out the side or coming out the north. Okay. So that's where the splitting of the actual wave itself comes in, not the splitting of the individual pieces that can be actually stored by an electron. And I guess I've run out of steam.
I got one last question, and then I think we should close because I got to
Yeah.
get going home. But I've got this diagram of the Lyman series, and we got the transition from n equals 1 to 2, 122 nanometers, and so we know exactly what frequency that is. It's going to be C
That's
divided by 100, and so what I'm hearing you say is that you could hit this first shell with something that the right wavelength, 122 nanometers, but just not enough energy to make the
Right.
transition happen.
Not enough pieces. Yeah.
And then when you get enough of those separate pieces to add up to the energy jump, then you jump from here to here. Is that what you're saying?
Yes.
Okay.
And it's like the water wave.
But there's a problem.
hitting a
with
post. Okay. The water wave hits a post. Okay.
Yeah.
It's just a piece of the wave that gives its energy to
I
that
see
post.
where you're coming from. Yeah.
Yeah.
But where
That's-
photons are
That's all my
different.
theory
They are
is.
at once spread out and particleized. So what I'm thinking here is this 122 nanometers. We know exactly what energy that frequency
Yeah.
has. It is E equals h nu. We multiply the speed of light divided by 122 nanometers times Planck's constant, and that is the energy of the photon that makes this electron jump.
No,
is
that's the
there is
energy
no
that makes
subdivision
that
of
photon
that
jump.
energy. E equals h nu. This 122 nanometers has one and only one energy that corresponds. You don't have 122 nanometers coming in at a quarter or a third of the energy. E equals h nu. Every photon that can
Yes.
create this transition has h nu of energy.
And that's correct. But they made the assumption that H was the smallest thing you could ever get. What happens if H is just the smallest thing we can actually experience, but actually H can be split?
Okay, so there's your hypothesis that you need to test is, can you get a smaller quantum than
And
H?
it's very difficult to do. So all I'm doing is taking what's logical and considering our first option of how that particle going through the two slits suddenly becomes a particle and decides it's going to hit here, here, here. And how does it always decide it's going to end up on the thing? And I know you explained that to me, but that I do not understand. And I don't believe that's a real explanation for what's happening there. Okay. It ends up there because the whole wave spreads across the whole screen, and just one atom, one electron will have 99% of that quanta in its possession. And when that little sliver comes along, the 100% of the quanta at the tail end, that atom will suddenly have 100% of the quanta and will jump to the next orbital or out of the atom if it's high enough.
All righty. So
Boy,
Gerry and Coffee have some interesting comments, so I can
Well, mine's really just informational, not a comment on the main thread of this.
well, stuff to
Yeah.
follow through.
and by the way, if you want to write me an email on it, feel free. And, great minds have been thinking about this for years. And I mean, I never expected to come up with this, but it was sheer accident in talking to my friends. We said, how could that possibly be? How can that electron or photon decide to end
It's a
up
good
on that
question.
spin?
It's a really,
And we said
The
there must be a
individual
better
electrons-
explanation for it.
The individual electrons do not decide. They come through and they hit the screen in connection with the quantum distribution that the wave functions give you. The wave functions are the wave, but they are not the particle.
I
And
agree. And the wave function is this thing. Well, I am not arguing about this thing. I'm
no,
arguing about the amount of these things that you have in order to do the job.
yeah.
Okay.
The thing
Yes.
of it is, the transitions are quantized. They are never fractional. And you can shine 120 nanometer light on that atom that in that diagram that
Okay.
Dave was showing, and it will never jump. It will never jump. You down
they have
up to
enough
122
frequency,
and
they
bang,
will.
it jumps.
Well,
And it's similarly for all the other interorbital jumps. In a way, you could think of a lump of metal as being a kind of stretched out horizontally and deep orbital. You want to think of it that way. And the electrons that are very near the top of the energy distribution in that, the ones that are going to get jumped out. But you
Yeah,
still
well-
have to get an individual photon in with an energy to make up the work function. Otherwise, it can't come out. You go over the work function and you get an electron, photoelectron, with an energy equal to the energy of the incoming photon less the work function. That's the same thing in a way as that picture of an individual atom in the orbitals. So
Well, I'd like to
it's the same
close
thing.
with just pointing out, Feynman remarking that at the quantum, subatomic level, it really is strange. And yes, the
Yeah.
math works beautifully, but we're having trouble getting the picture. And Joe's picture of the wave hitting just a pebble on the beach, that's one of the pictures Feynman's talking about.
Yeah.
So
And
it is a mysterious topic, but I think we've got
yeah,
gone as far as we're going to get
we
tonight.
kind of
But thanks
done
for
this
coming,
long
everybody.
enough. Let the bruises heal.
All righty. So yeah, we'll see you next time. Thanks for participating. Thanks a lot, Joe, for doing all that work on our behalf.
thank you, everybody. I really appreciate your time and looking over and your comments. Thank you.
All
Okay.
righty.
Yeah.
Well, take care, everybody.
And I hope you read my paper.
Yeah.
Okay. And by the way, if you know anybody else that's interested in it, that might be interested in reading my paper or seeing my
Yeah. Well,
slides.
once this goes on YouTube, you can point your friends to that, and here's the whole
Yeah.
discussion.
Okay, great.
Alrighty.
Thank you.
Take care, everyone.
Good night,
Live
everybody.
long and prosper.
Thank you.